C is one of the most influential programming languages ever created. It's the backbone of countless popular software applications. C was also one of the first programming languages I learned. In this video, I'm sharing 7 essential facts about the C programming language. C does not support object-oriented programming, anonymous functions, exceptions, list comprehensions, and many other advanced programming concepts found in other popular languages. As a result, C's syntax is relatively straightforward and minimalistic. The complete documentation for the current version of C, including explanations and examples, is remarkably compact. The language syntax reference takes up less than 160 pages. Even the standard library, which is available to all C programs, is relatively small, adding up around 370 pages to the documentation. All this makes C quick to learn and use. Before your C code can be executed, it gets transformed by a compiler infrastructure into executable code that runs directly on the system's hardware. This process begins with preprocessing, where the preprocessor handles directives like include and define. For instance, it replaces include stdio.h with the content of the stdio.h file, incorporating the declaration of the function puts. Next, the compiler translates the preprocessed code into assembly code specific to the target platform, optimizing it if needed. Then, the assembler converts this assembly code into machine code, generating object files that the system's hardware can understand. Finally, the linker combines these object files and any necessary libraries into a single executable program. The result is a binary file that the operating system can run directly, without the need for a virtual machine or interpreter. This also means that C is platform dependent, so you need to compile different binaries for different architectures like x86, ARM, etc. Different operating systems prefer different default compiler infrastructures to transform C code into binary. For Linux, it's GNU GCC. For Mac OS and FreeBSD, it's Clang. For Microsoft Windows, it's MSVC. But here's the kicker. Except for MSVC, these compiler infrastructures can be used across different platforms, giving you flexibility in your development environment. The big advantage with C is performance. Since it's compiled to native machine code, C programs run much faster compared to interpreted languages like Python or JavaScript. For example, a simple matrix multiplication with 1000 rows and columns can be orders of magnitude faster in C. So, if you need your programs to run quickly and efficiently, C's native execution is a great choice. One of the great strengths of C is its extensive support for provided libraries. These libraries provide header files that define macros, global variables, custom types, and declare functions. The actual implementations are in library files. The C documentation defines the standard library, a collection of essential functions and macros for convenient coding, available to all C programs. Many header files are ready for you to use in your C programs. These header files contain, among other things, declarations of input and output functions, general utilities like memory allocation and process control, string handling functions, mathematical functions. Please note that on freestanding C environments, systems without a full operating system, often found in embedded systems or low-level programming contexts, only a minimal subset of the standard library is provided. This section focuses on hosted environments, which are systems with a full operating system like Linux, Mac OS, or Windows, where the full standard library must be available. On Linux, the standard library is typically part of the GNU C library glibc. On Mac OS, it's part of the Apple C library libsystem. And on Windows, it is part of the Microsoft C runtime library MSVCRT. Each operating system has its own standard library implementation because they do not share the same system API or system call interface. System calls are the interface between your C programs and the operating system. These are often referenced in standard library functions, bridging the gap between user space programs and the operating system. Since most popular operating systems like Linux, Windows, and Mac OS are written in C, they provide extensive system call interfaces in C. For instance, on Linux, you might use the linux/io_uring.h headers functions to work with asynchronous I/O. On Mac OS, you might use the sys/event.h header file. On Windows, you will use the windows.h header file. Your C program can directly make system calls declared in these kernel headers. However, this can lead to portability issues because operating systems do not provide the same interfaces. Consequently, each program will have to handle all targeted operating systems specifically. This situation arises because the C standard library, intentionally small, does not implement all features provided by operating systems through system calls, focusing only on the most common system-related features. To reduce these portability issues, the POSIX library, standardized by IEEE and the Open Group, was created to unify Unix-like operating systems by providing a standard set of APIs. Think of it as a complementary C library to the standard library, offering features common across Unix-like systems, but not mandatory. The POSIX standard includes, among others, headers for thread management, function definitions for various system calls like fork and read, asynchronous input and output, network operations definitions, pattern matching. POSIX ensures that programs can be more portable across different Unix-like systems, reducing the differences that developers need to handle. Many operating systems, including Linux and Mac OS, support POSIX. Linux and Mac OS POSIX libraries are included in glibc and libsystem, respectively. By using the POSIX library in your code, you can address portability concerns when targeting systems that are POSIX compliant. To keep your C code portable, use the C standard library first, the POSIX library if needed, and direct system calls only as a last resort. Learning C helps programmers understand how computers work. As you learn and use C to develop software, you will need to use the operating system interface or the POSIX library to make low-level calls. This will help you gain a better understanding of the operating system and its interface. Computer memory. Learning C can help you understand program memory. Here are a few aspects of it. Stack memory layout. In the program, two int variables x and y are defined with x defined before y. A pointer p is assigned the address of x. By manipulating and accessing memory through the pointer p, we can observe the layout of variables on the stack. We modify the value of the memory location at the address following x and observe that the value of y changes. This suggests that y is laid out at the higher address right after x. Memory representation. We can also understand how integer data is represented in memory with the following example. The program assigns the hexadecimal value 0x41424344 representing A, B, C, D to an integer v. The char pointer p is then used to access each byte of v. By printing the memory locations pointed by p, p+1, p+2, and p+3, you can see how the integer is laid out in memory. The output reveals whether your system uses Little Endian or Big Endian byte order. In other words, whether the integer's least significant byte is stored at the smallest address or the highest address. Running this example on my x86 computer outputs DCP8, suggesting that it is a Little Endian. C's simplicity comes with trade-offs, which can make developing software in C challenging. These challenges are related to safety, the ability to easily write reliable code, and features, things that increase productivity. Safety. Memory safety. C does not provide built-in memory safety, which means developers need to manually manage memory. This can lead to common issues like buffer overflows where a memory location is improperly accessed through a pointer. Use after free errors where an address is used after the underlying memory is freed. Memory leaks where allocated memory is not freed. These bugs are often difficult to detect and can lead to security vulnerabilities. Standard library functions. C's standard library contains functions like printf and string copy that can be easily misused. For example, using printf without proper format specifiers can lead to undefined behavior. Similarly, string copy does not check the size of the destination buffer, which can cause buffer overflows. Here, the copied string, longer than A, overruns it and overwrites B. Error handling. Error handling in C can be confusing because there is no standard way to handle errors. Different libraries and functions use different conventions, such as returning -1 or null to indicate an error, which can lead to bugs if not handled consistently. For example, the POSIX make-tier call returns 0 on success and -1 on failure, while the OpenSSL type print CTX function returns 1 on success and 0 on failure. A developer working with both can easily confuse the error codes. Features and tooling. Lack of modern features. C lacks features like object-oriented programming, templates, and traits, which can make it more difficult to build complex applications. Developers often have to implement these features manually, which can be error-prone and time-consuming. Reliance on third-party libraries. C has a very small standard library, so developers often rely on third-party libraries for data structures like hash maps, dynamic lists, and more, web development, and more. This can lead to dependency management issues and potential security vulnerabilities if the libraries are not well maintained. No default testing tools. C does not come with built-in testing tool, which means developers need to create their own testing frameworks or use third-party tools. This absence of integrated solutions can introduce extra complexity and effort into projects. No default package manager or build tool. C does not have a standard package manager or build tool, which means developers need to choose from various options like BC Package, Conan, and even System Package Manager, as well as Auto Tools, SMake, or Visual Studio build tools. This can lead to inconsistencies and compatibility issues across different environments. C was originally developed at Bell Labs by Dennis Ritchie in the early 1970s to enable Unix's transition from assembly to a higher-level language, a task carried out with Ken Thompson. It was first released around 1972. Early on, features were added to the language as needed based on Unix development requirements. However, there was no standardization, and different compilers implemented their own version of C, leading to code portability issues. In 1978, Prime Kernighan and Dennis Ritchie wrote the original description of C in a book that became widely recognized, the C programming language, also known as the White Book. This book served as the informal standard for C, referred to as KNRC. The first formal standard for C was established in 1989 by the American National Standard Institute, ANSI, and called NCC, also known as C89. It introduced several changes to KNRC, such as the automatic definition of SDDC macro, which indicates when a program is compiled using standard C. This macro is defined by the compiler for standard C code, but is not set for non-standard variants like KNRC. Shortly after, NCC became ISO C C90 when the International Organization for Standardization, ISO, took over the C language standard. For most compilers, C89 and C90 are effectively identical. In 1995, a new version of the C standard, referred to as C94, C95, or EMD1, was published. It introduced few amendments to the C89/C90 standard, including the stdc version macro, which identified the C standard version being used. Versions of C from C95 onward define this macro, setting its value to a long integer that corresponds to the year and month of the standard. This version also introduced digraphs, which are special character pairs used to replace certain symbols. For keywords missing keys like square braces and curly braces, and even the hash sign, digraphs provide a convenient alternative, as shown in this table, where a symbol is replaced by a pair of characters. A simple Hello World program will be typed like this using digraphs. In 1999, major updates to the C standard were made, resulting in C99. This version introduced several new features, such as inline functions, variable length arrays, single-line comments, Boolean macros, and improved support for floating point arithmetic. It also removed implicit declarations. In 2011, another standard, C11, was released. It was marked by the removal of the unsafe gets function. Additionally, several features were added, including compile time assertions. The next standard, C17, was released in 2018 as a corrected version of C11. It introduced no significant new features or removals, aside from updates to the std version macro value. For most compilers, such as GCC, the only difference between C11 and C17 is this updated macro value. The current version of the C standard, C23, was released in October 2024. This version included numerous deletions and additions. For example, the key-nr style function definition, where parameter types are specified after the parenthesis, was removed. At the same time, new constants, preprocessor macros, and keywords were added. To date, there are 5 major C language standard versions: C89, C95, C99, C11, and C23. Future versions are expected to continue evolving the language. When compiling a program, you can specify the desired standard using the corresponding compiler flag. Some compilers like GCC implement extensions to the C standard, such as GNU-C. These extensions can also be specified when compiling programs, provided the compiler supports them. Ever wonder why C is often confused with C++, C#, and Objective-C? While they share the common heritage of C, they are fundamentally different programming languages. C# draws inspiration from C but is tailored for the .NET framework. It's a completely different language with no compatibility with C. C# is compiled into an intermediate code and runs on a virtual machine, offering a different execution model from C. It incorporates modern features designed to simplify development and enhance productivity. C# is mainly used to develop Windows applications. Both C++ and Objective-C are direct extensions of C, adding new features while retaining compatibility with C code. They both introduce object-oriented programming and exception handling in different forms, allowing developers to create more complex and modular applications. They also provide additional I/O features like C++ cout and Objective-C's nslog. Objective-C additionally brings dynamic typing, messaging, and more. Its ID type adds flexibility, allowing for more dynamic code practices. Objective-C is mainly used for macOS and iOS development. C++, on the other hand, brings in features like templates. One interesting aspect of C++ is name mangling. When you compile a function in C++, it encodes additional information into the name of the function in assembly code, including the length of the function name and the identifiers of the parameter types. This allows for function overloading, meaning you can have multiple functions with the same name but different parameters, something you can't do in C. When referring to C libraries from C++ code, you often need to use extern C to prevent name mangling and ensure the C library functions are correctly linked. While C++ and Objective-C retain compatibility with C code, The reverse is not true. C++ and Objective-C code cannot be compiled as C due to their additional features and syntax. To wrap up, here are the key takeaways from this video. C's minimalistic design makes it accessible and efficient. Its machine code compilation ensures high performance. C offers flexibility through standard, system, and POSIX library. Learning C deepens your understanding of computer systems. Its simplicity comes at the cost of safety and modern features. Decades of evolution have refined and standardized the language. C stands apart from C++, C#, and Objective-C, despite their shared origin in the C programming language. With its balance of power and simplicity, C remains a cornerstone in programming and will continue to be relevant for years to come. Thanks for watching, and I hope you've gained valuable insights into this foundational language. Please like this video, subscribe, and check out the description section for additional resources to help you pursue your software engineering journey faster and easier.